You tested positive, and yet you're most likely not sick. One day, a phone call comes in from the hospital. On a screening test for a disease that strikes about 1 in 1,000 people, you've come back positive. Look it up, and you'll find this test scores a 99 on 2 separate skills. By any measure, a superb test. So here's the question. Most people answer like this. 99% obviously, didn't they say it's 99% accurate? But the real answer, hard as it is to believe, is somewhere around 9%. Where did the 99 go, and how did we land on 9? It's not a typo. No shame in getting it wrong. Doctors at Harvard Medical School blew it in droves too. This mismatch has a name: base rate neglect. No scary formulas ahead. These are all the tools we'll use. In 1978, a short report appeared in medicine's most prestigious journal. At 4 Harvard teaching hospitals, 60 doctors were given a single question. The question went like this. The prevalence is 1 in 1,000, and the false positive rate is 5%. 27 of the 60, nearly half, answered 95%. Only 11 people reached the correct answer of about 2%. It wasn't a one-off. 1982, the breast cancer screening problem. In 1998, too, when the question was posed in probabilities, only about 1 doctor in 10 got it right. These doctors aren't people who can't do arithmetic. Nearly every one of them erred in the same direction. The culprit was the first line of the problem, the 1 in 1,000 that everyone skimmed past. Captivated by the vivid positive right in front of them, they dropped this underlying rate entirely. But there's hope. When the same problem was asked in counts of people instead of probabilities, the success rate jumped to nearly half. So let's take that path too. Drop the probabilities and count people. Let's go back to the screening problem from the intro. This time we'll count it out for ourselves. We line up an entire city of 100,000 people at the testing center. Step 1, count the disease first. 1 in 1,000, so out of 100,000 people, 100 are truly sick. Before the test even begins, the world is already tilted like this. That's the base rate. Step 2, test the patients. With 99% sensitivity, 99 out of 100 come back positive. Step 3, the healthy people. 99% specificity flipped around means 1% get wrongly flagged. 1% sounds like nothing, but the pool is 99,900 people. 1% of that is 999. Step 4. Gather everyone who tested positive into one room. 99 plus 999. In this room, the true patient's number 99. So the probability that a positive is a real patient is. That's all there is to it. 2 multiplications, 1 division. The problem that toppled Harvard became grade school arithmetic. Let's see it as a picture. On the left is a frequency tree, where 100,000 people split into 4 boxes. The positive waiting room on the right is a sea of orange. Of the 1,098, 999 are healthy people who were wrongly flagged. The true patients are the 99 in red, about 1 in every 11. 99% accuracy is no lie. Both skills genuinely score a 99. The moment a tiny 1% error rate meets a huge pool of 99,900 people, the 999 wrongly flagged overwhelm the 100 true patients by nearly 10 to 1. Here's what's worth noticing. This orange C has almost nothing to do with sensitivity. What made the C is specificity's 1% gap, multiplied by a pool of 99,900. Now we know where our intuition slipped. There were actually 2 questions hidden inside. It looks like just the word order flipped, but these are completely different questions. Base rate neglect, in the end, is the habit of pasting the first answer onto the second question. Evidence doesn't erase the base rate. It has to be read on top of the base rate. The Harvard problem from Chapter 1 solves on the spot too. Line up 1,000 people. The 1 true patient tests positive. And 5% of the 999 healthy people, about 50, come back positive too. Of 51 positives, only 1 is real, about 2%. The doctor's 95% was an answer inflated 50-fold. But this illusion doesn't live only inside hospital walls. Let's head to the courtroom. It comes from psychologists Kahneman and Tversky, the single most famous problem in the whole field. By mapping out the flaws in human judgment with problems like these, Kahneman went on to win the Nobel Prize in economics. One night, a cab hits someone and speeds off. In this city, 85% of the cabs are green and 15% are blue. A witness testifies it was blue. The witness is 80% accurate. So what's the probability it really was blue? People's answers clustered around 80%. Look familiar? They copied one number straight across and let the base rate that 85% are green evaporate. By now we know how to find the answer. Instead of people, let's replay 100,000 nights when an accident happened. In the mosaic on the left, each column's width is the base rate. Green 85, blue 15. Blue cabs cause accidents on about 15,000 nights. On 80% of those, about 12,000 nights, the witness correctly says blue. But green cabs account for a full 85,000 nights, and misjudging 20% of those turns about 17,000 nights into blue. Of the roughly 29,000 nights that drew a blue testimony, only about 12,000 were truly blue. Even when the witness tells the truth, green is still the more likely culprit, at 59%. There are simply so many green cabs that the nights when green is misread outnumber the nights when blue is seen right. So why on earth does our mind throw the base rate away so consistently? The culprit is the representativeness heuristic. Instead of probability, it serves up resemblance as the answer. Resemblance is fast and vivid, but it has a fatal blind spot. Resemblance can't see head count. A 1973 experiment. People are told that one person was drawn from a group of 70 engineers and 30 lawyers. The instant a vivid little story is tossed in, the drab statistics switch off on their own. Shy, meticulous, and a lover of books. Librarian or farmer? The description resembles a librarian, but at the time, male farmers outnumbered male librarians 20-1. The good news: wrap a base rate in a causal story and people do factor it in fairly well. The prescription is clear. To revive a base rate, turn it into a story about headcount. At this point you might want to leap to the conclusion that tests are all worthless. That too is wrong. What a positive result means isn't a fixed number. Two dials set it together. The curve on the left shows how the meaning of a positive rises as the disease grows more common. Our scenario, 1 in 1,000 with 99% accuracy, sits at the 9% point on the left slope. Even if you swap in a top-of-the-line 99.9% test, against this disease it lands at exactly 50%, a coin toss. At this point the true patients and the wrongly flagged meet in exactly equal numbers. Flip it around. As the disease grows common, the same 99% test suddenly starts doing its job well. In short, more than half of what a positive means is decided by the group being tested. The very same test, aimed at an entire symptom-free population, becomes a false positive factory. Used on people who already have symptoms, it becomes a tool you can trust. And in the rare disease range, the dial that lifts the meaning of a positive is not sensitivity but specificity. Push sensitivity to 100% and 9% only becomes 9.1%. Push specificity to 99.9% and it leaps to about 50%. Now for the most hopeful scene in this whole story, the ladder of retesting. The first positive gave us 9%. But that 9% isn't despair. It's an updated base rate. You've just moved out of the 1 in 1,000 group and into the 1 in 11 group. On top of this new base rate, an independent second positive brings it to about 91%. A third sends it soaring to 99.9%. That's why a positive on a screening test is always followed by a confirmatory test. One line of fine print, though. This ladder only holds when the two tests are independent of each other. This fallacy isn't a textbook quiz. It's a phenomenon still very much at work today. The 2017 Champions League final in Cardiff. Police facial recognition became a living case study. Among tens of thousands, wanted suspects are a tiny few. With the base rate at rock bottom, most of the alerts have to be false. Credit card fraud detection is the same. Fraudulent transactions are a tiny fraction of the total. DNA in the courtroom. The chance that an unrelated person matches by coincidence is said to be 1 in 1 million. The jury hears it as a 1 in 1,000,000 chance of innocence. But in a population of 10 million, coincidental matches number 10 people. This error, quietly rereading the number the test gave you as the number the jury wants, has a name. There have been real cases where a misread statistic helped secure a conviction, and the Royal Statistical Society even issued a formal statement about it. The late-night self-diagnosis. That headache may resemble a terrifying disease, but the overwhelming majority are just headaches. It doesn't mean ignore the rare possibility. It means reach for the common one first. Make the base rate your starting point. What we did, in the end, was repeat one single move over and over. Gather every candidate the evidence points to into one room, then count what fraction of that room is the real thing. This finger counting has a 250-year-old name, from a clergyman and amateur mathematician, Thomas Bayes. This is Bayes' theorem. The symbols may look unfamiliar, but put into plain words, it's something we already know. The probability that a positive is a patient equals the probability that a patient tests positive, times the probability of being a patient in the first place. All divided by the probability that anyone at all tests positive. And right there in the numerator, the base rate sits multiplied in. Base rate neglect is the habit of quietly pretending that term isn't there, and Bayes' theorem is its formal antidote. Plug the opening problem straight into the formula and boil today's journey down to a single card that fits a phone screen, and here it is. The antidote comes in 2 pills. Turn probabilities into head counts, and ask about the base rate first. So the next time some shocking news comes your way, teach your startled heart to ask this first question. That one question turns 99% into 9%, and 80% into 41%, cutting an inflated world back down to its true size. If you enjoyed today's story, hit subscribe and like, turn on notifications, and I'll see you in the next one.